Hi, I'm Tom, amateur reader call sign N8FDY, and today it's time for another meter review. This time we're doing the Uni UT161E. Let's see what is in here. All right, comes with a nice case. I applied this label myself because I have a few of these Uni T cases with different things in it, so I like to know what's in them before I open them up. Comes wrapped in some cellophane. Little Ziploc bag here. So here's the meter. It comes with an adapter to test transistors. It comes with a USB optical interface. It comes with a set of leads that are plastic, but they are gold plated. It also comes with a screwdriver to change the batteries or the fuses. That's all this comes with, and of course, manual. But I bought the extra optional Bluetooth interface because this will connect to the Bluetooth interface, the same place that this would connect. So you can either use your PC, Windows only software of course, or you can use your Android or iOS device with this. So let's put all this back. I bought this off of Amazon, and I specifically bought it from the Uni T Direct store, and it was $128.77. Specifically made sure it was from the Uni T Direct store because if you buy it from them, you get an 18-month USA warranty. So that is pretty handy. Let's see what the features of this meter are. It's third-party tested by ETL for Canada and the US. It's category 4, 600 volts, and category 3, 1000 volts rated. It's a 22,000 count meter. Its basic DC accuracy is 0.05% plus 5. It has a 46 segment bar graph. It does true RMS. It has a min-max function. It has the relative or delta function. It has a low-pass filter for AC voltage measurements. It comes with 4 AAA batteries. And it has the 18-month warranty if you get it from the Uni T Direct store. So that's a pretty good set of features. And you are paying a little bit more than the other meter we reviewed. The UT161D was only a 6,000 count meter, and its basic DC accuracy was 0.5%. So this is a magnitude better DC accuracy. Plus, since it's a 2200 count, we'll see how that affects the resolution here. First, we'll start out with DC volts. Now, when you turn the meter on, you can hold down the select button to deactivate the auto shutoff because we don't want it to turn off on us. This is 2.5005 and it reads 2.500, so that's right on the nose. This is 5.0009 and it reads 5.001. So I think that's okay because it rounded up because the digit you can't see on there was a 9. So If you round it up a little bit, you get the 001. Here's 7.5018, and it reads it as 7.502. Again, I think a roundup is fine for this meter. Here is 10.0015, and it reads it as 10.002. Again, rounding up is perfectly fine. Now, let's take a look at the other DC voltages I measured. And also, there is a written review where these measurements will be listed. And that review is available. The URL is in the description of this video. And it's also on my GitHub site. Well, we measured in the millivolt range all the way up to 600 volts. And all the voltage measurements met the specifications as stated in the manual. And you notice that from 1 volt to the 220 volts, it's rated at 0.05 plus 5. For the millivolts, it's rated at 0.1, so a lot less accurate. And it's also, anything over 200 volts is rated at 0.1. But that's okay, because the sweet spot of where we're going to use this for most electronics is in the 1 to 20 volt range. The DC input impedance was 11 mega ohms for the voltage range and 13 mega ohms for the millivolt range. Now we're going to do some AC voltage measurements. The one I'm going to do here is using the DMM check, and I'm using the 5 volts 100 hertz square wave, and we'll see what the AC voltage is. We're getting 5.0078. It's kind of fluctuating. It should be 4.9987 volts. But that's pretty close, because DC accuracy is much better than AC accuracy at most meters. Let's take a look at the other AC measurements I made earlier. Millivolt range is rated at 1% plus 10. And the voltage range is rated at 0.8% plus 10. But all the readings met the specifications as stated in the manual. AC voltage 3 dB cutoff was 778 kilohertz. That is pretty good. You can definitely cover the audio range and some IF frequency ranges in radios. Now, this meter also claims to do AC plus DC, but that is misleading, because most meters that say they do AC plus DC will compute the value, because it's basically you have to take the AC and square it and take the DC and square it and then take the square root of that total, and that gives you the true RMS AC plus DC. But this meter doesn't really do that. When they say they do AC plus DC, they just switch back and forth between the AC reading and the DC reading. So if you really need a meter that can do that, this isn't it, because this doesn't compute it. You still have to use your calculator. Now, let's do some current measurements. First, we'll start out with the AC current. There's a little inconsistency with the meter. On the millivolt range, you have to switch between AC and DC, and it defaults to AC when you first go to that. But on the current ranges, it defaults to DC. So we're going to have to switch this over to AC so we can monitor this current. This current is 0.999 milliamps, and it reads 0.999. That is excellent. Now we will do some DC currents. This is 0.89 microamps, and the meter reads 0.92. Pretty close. Here is 9.21 microamps, and the meter reads 9.23. Kind of can't make up its mind between 3, 4, and 5. Here's 99.0 microamps, and it reads it as 99.03. So that's pretty close. Here's 131.8 microamps, and it reads it as 131.87. That is good. I'd like to point out that some meters, or many meters, are less accurate at the low end of their range, the first 10%, or some of them the first 20% of the range. It is less accurate than the rest of the range. This is 1.00 milliamps. It reads it as 1.011. But again, this is the low end of the range, and still that's pretty good. Here's 9.98 milliamps, and it reads it as 9.995. A little off. Here's 99.4 milliamps, and it reads it as 99.43. So that's right on. Now let's take a look at the other currents I measured. Well, as you can see by the green highlights, all the measurements met the specifications as stated in the manual. The shunt resistors for the amp range was 0.02 ohms, for the milliamp range was 5.89 ohms, and for the microamp range it was 491.36 ohms. The microamp range, that seems pretty high. Most meters are around 100 or so ohms in the microamp range, but this is 5 times that, so that'll definitely affect your readings if your circuit that you have this inserted in is sensitive to that. If it's a low impedance circuit, it will be sensitive to that resistance. Now we're going to check some resistance values. First, let's zero out the leads. Got to have the leads in the right place, though. Okay, somewhere between 7 and 8 and 6. Back and forth, back and forth. Well, let's make sure these are tight. Connected well. And it's still... this meter does seem to be a little more erratic than most. So we'll just delta this out and see what happens. All right, we picked 9. This is 1.004 ohms, and it reads it as 1.02, or 1.00. Again, in this ohm range, it's pretty jumpy. Here is 10.007, and it reads it as 10.0342. It's almost, you're going to have to kind of ignore the last digit. Oh, I should mention that the way I know what these measurements are is I've taken all the voltage measurements, current measurements, resistance, capacitance measurements with a Keithley DMM 6500 that was calibrated at the beginning of the year. So that is what I'm using to mark down what these values are, and that's what I'm judging all the meters with. The Keithley should be about 10 times more accurate than any of the highest rated meter I'm using here. So it's a pretty good indication. I know it's not like having voltage standards or having a calibrator, but I don't have any of that, so I'm just testing these meters the best way I can. Here is a 100.069 ohm resistor, and it reads it as 99.99, or, well, 99.90. Like I said, it's jumpy on the last digit. Here's a 1.0001 kilo ohm resistor, and it reads it as, since we're in the relative or delta mode, and we did that in the low ohms range, it won't allow you to change to a higher range. It turns off auto. So let's turn the rel off. And it goes back into auto. And now we get 1.0002 kiloohms. So that's pretty close. Here's a 10.002 kilo ohm resistor, and it reads it as 9.999. Pretty close. Here's a 100.02 kilo ohm resistor, and it reads it as 100.01. Again, very, very close. On these higher resistances, it's a little more stable reading. Here's a 0.997 mega ohm resistor, and it reads it as 0.9937. Here is a 9.97 mega ohm resistor, and it reads it as 9.9, and the last two digits are fluctuating. Here's a 100 mega ohm resistor, and it's reading it as 97, and the last two digits are fluctuating a lot, but 90, 98, 97. It's okay, because this is one of the very few meters I have that can read up to a 100 mega ohm resistor. Of course, the bench meter can. Portable DMMs, there's very few of them that can go up to the 100 mega ohms. So, I have to give them credit. It's may be a little jumpy, but at least it's trying. Well, let's take a look at how it fared with the accuracy on these resistance measurements. Well, as you can see by the green highlight that all the resistance measurements met the specifications that are stated in the manual. It used, on the low range, 3.2 volts to test the resistance. The medium range was 1.21 volts, and the high range used 0.61. Now we're going to do some capacitance readings. As you can see, the leads have a stray capacitance of, well, let's get them over here like that, like we're going to use them. It's reading a stray capacitance of about 9 picofarads. Let's see, 10 picofarads. Let's roll that out and start doing some measurements. In my new measurement protocol, I pretty much skip these 10 and 100 picofarad ceramic capacitors, because almost all the meters get them wrong. So we're going to start with a 1 nanofarad film capacitor. Here's a 1.005 nanofarad, and it reads it as 1.015. That's not too bad. Here's a 9.921 nanofarad capacitor, and it reads it as 9.93, and the last digit's fluctuating. Here's a 99.51 nanofarad capacitor. Oh, and it's over range because we use the rel function to null out the lead capacitance. And when you do that, it locks it into a manual ranging. So we have to turn off the rel function, and then it turns auto ranging back on. And it reads this as 100.06, which is pretty close. Here's a 1.009 microfarad capacitor, and it comes out as 1.014. That's pretty close. Now we're going to the polymer capacitors. Here's 10.294 microfarad capacitors, and it reads it as 10.955. Here's a 112.2 microfarad capacitor, and it reads it as 111.61. Oh, now it's 65. 64. It's drifting a little bit. Here's a 944 microfarad capacitor, and it reads it as 1.0149 millifarads, which is equivalent to 1014 microfarads. Let's take a look at how the accuracy of these capacitance readings fared. The readings met all the specifications as stated in the manual. Now it's time to test some diodes. Here is the red LED with the forward voltage, and you can see that there's the green light on, and they're also chirp. So let me show you the chirp. So chirp and green light, that's pretty good. And it lights the diode. Let's see what it does if there's a short. So if the diode is shorted, it's going to turn red and beep at you. Here's the yellow LED with the forward voltage. Here's the green LED with the forward voltage. It's a little dim. So here's the Schottky diode with the forward voltage. And again, it chirps. Well, with all of them, when the light turns green, it chirps. Let me let you hear that again. That's pretty nice. And it works on LEDs. Here's the small signal diode with forward voltage. And here's the rectifier diode with forward voltage. The max diode voltage is 2.98 volts. And the max diode current is 755 microamps. Well, that could be why the green one was a little dim, because that's really not much current. Now it's time for continuity. So we had to bring out the probe masters. Let's see how this goes. Well, that worked way much better than its little brother. The 161D had a kind of weird way it did, but this is fine. It does delay. The beep starts before the green light comes on. But if you need to watch it, that could slow you down. But if you can, let's try, see how fast it goes. Okay, pretty fast. Let's try that again. Let's see how fast it goes. That's pretty fast, but the light doesn't work when you're doing it fast, so. But I like it. They have gold-plated leads, so let's try them. You may not have to buy leads with this meter because they came with gold-plated leads. It's still pretty stiff plastic though, so if you want the nice silicone, you may have to spring for good leads, but you won't have to spring for them because of the gold plating. I hope. Let's see how they do with continuity. That usually lets you know how the tips are. That's a good sign. Let's try. All right, that worked pretty good. Well, this meter doesn't do temperature, which is unusual because most of the meters I've been reviewing do. There's a few that didn't, but this one does not. But in place of that, it measures transistor DC gain. And I don't know how useful that is, but it does do it. And we'll just show you that now. It comes with this adapter, and the left side is NPN, the right side's PNP, and you put it over in what's called HFE, and if you look that up on the data sheets of the transistors, it calls it the DC gain. Now some people call this beta, and it shows up, there's a little beta on the screen. Let us show you. I have a NPN transistor. It's a 2N3904. I have two of them, so you can see if there's a difference. And their DC current gain in the specs say it should be anywhere from 100 to 300. So you got to line of course, the emitter base collector in the right holes here. All right, we got the emitter base collector in the right holes, and it says 178. And the spec sheet says it should be anywhere from 100 to 300. So 170, well, now it's 176, 75. I did notice that it seems to drift down. So that's one of them. Let's try this second one. That's 180. So pretty close to the other one. And it's within the 100 to 300. Now that spec was for 10 milliamps, but I don't know if this is putting 10 milliamps through it or not. They don't tell you in the documentation how much current it uses. And just to show you that the PNP works, I got a PNP out. This is a 2N3906, so it's again 100 to 300, and this is a PNP, and you got to get the emitter base collector put in the right holes. This one, it's 149. And again, that's right in the middle. So there's your HFE measurements. I don't know how useful they are to you. And you give up temperature measurements. But if you need a meter that does that, that's what this one can do it. I can't tell you how accurate it is because I don't have another meter in the house that can measure this. Since you give up temperature measurements, I actually consider this a negative. Let's look at the accuracy specification of this meter and see how they compare to the other meters. This is a group of meters that I used to present at a amateur radio club meeting. So it's a varied bunch, and I wanted to include this one because I thought it was a good value, and they are a value-sensitive crowd. So it's $128.77, and what you get is a 22,000 counts. Now the accuracy specifications compared to all these other meters, it's definitely not the worst, except in DC amps it was the worst. But it's a good middle-of-the-road meter. If you want to get a little more accuracy, you do have to start going up the chain. I would say that the EV blog BM786 is starting up that chain of better accuracy. But I'd say for $128, it's definitely a notch above the lower cost meters. Now if we look at the resistance and capacitance range, then it's a little different story because the high resistance and all the capacitance ranges except one are the worst specification. If that isn't your focus, this meter should be fine. This meter can do logging, and you can log to a PC with the included USB interface, and it runs on Windows 10. And I tested it on Windows 10, as you can see here. You can also buy an optional Bluetooth interface, which I did, and it will work with iPhone and iPad. It says it'll also work with Android, but I have an Android tablet, and it didn't work on that because it wanted GPS for some strange reason. Well, here we have the battery compartment, and as you can see, it has one captive screw, which is very handy, and it has the 4 batteries, and the fuses are accessible, so that is very handy. And it uses a 11 amp fuse and a 600 milliamp fuse. Now let's get into the pros and cons of this meter. The good parts of this meter: it's third-party safety tested by ETL. It's the lowest cost meter that I've found that is 0.05 +5 DC accuracy. All the measurements taken met the accuracy specifications stated in the manual. It includes the USB interface, and the software to use it is freely downloadable from their website. And for a reasonable $30, you can get the Bluetooth adapter, and the software is free to download from the app stores. The only bad parts of this meter that I see is that the microamp shunt resistor is higher than normal. Like I said, most meters are around 100, and this one is around 500. So that's a concern if you're interested in microamp ranges. It beeps every time you move the rotary switch, which I don't like that, but that's what it does. And you can't measure temperature with it. To sum it up, I would say that if you're looking for an entry-level beginner's meter and you want something a little better and you can afford something a little better than its little brother, you might want to look into this one. I would say that lack of temperature measurement could be a concern. It's definitely more accurate than little brother, but it's also costs you about $28 more. So if you're interested in this meter, take a look at the written review and see what you think, and this might be the one for you. Anyway, we have plenty more to review, so you might discover some other one that's even better. So this is Tom, N8FDY, saying 73 and take it easy.